So, we have done, we're going to ignore cross sections for a while because that's a different approach, and we'll come back to the cross section problems tomorrow. I don't have time today to talk about them, but they do warrant some discussion. We'll save that until tomorrow. So, the problems we've solved so far using discs and washers all have one thing in common, and that is your representative rectangle is perpendicular to the axis of revolution. What if your representative rectangle is parallel to the axis of revolution? And if you do that, you get something called the shell method. There's a lot of derivation in this slideshow, so just try to be patient and bear with me until I get to the examples, and then things will make sense. Okay, so we're going to use the shell method. We're going to compare the disk method and the shell method, which is why the reason I gave you that worksheet on cups for Fisher-Price, because you'll be able to look at what you've already worked on for the disk method.
I forgot my pen.
Hey everybody, it's Drew.
Hi, Drew.
What's up, buddy?
I forgot my pen. Thank you.
Supluma is supluma. C. Drew's leaving, everybody.
Bye, Drew.
See you tomorrow. No, I won't really, but that's okay. And then you should be able to perform CPR on someone in these. How many people are certified in CPR? Awesome, that makes me feel better as I get older.
I think we have to.
For what?
There was a story to that.
Is that a graduation?
No, but like, after 99%.
Mr. Reedy, can I tell you a funny story about it?
We really are.
It'll be like super quick, less than a minute. Okay, so I wasn't there the entire week that we were learning how to do CPR, right? So the day of testing I came in, and she was like, okay, I know you're like signed up for it, but you don't have to do it today. You can just like sign your name up right now. So I signed my name up to do it like on her actual computer, but I accidentally deleted every single person's name and information. So everyone had to re-put it in, and she got really mad at me.
Gee, I wonder why.
And she's like, just do it on Monday. And I was like, I don't want to do it anymore. She's like, just do it on Monday. I'm like, no, it's fine, it's good. She's like, no, just do it on Monday. I'm like, no, So I never actually did it, so I'm not certified.
Thank you for sharing. You feel better now?
Yeah.
Good. Okay, so as I mentioned, what if the representative rectangle is parallel to the axis of revolution? Let me show you a picture of what that looks like. For those of you that are visually challenged, we'll go back into this cool program. Okay, so these we talked about already. The blue one was the disk. If we move it off the axis, we get a washer. However, here I have a big red representative rectangle that's parallel to the axis of revolution. So when I spin that thing, I get that.
That is pretty less, yes.
That thing is called the shell. You can find the volume of a shell by taking the cylinder and subtracting the hole through the center. That would mean that we need two different radii. The distance out to the outside of that shell and the distance to the inside of that shell. So we're going to get around that by doing some tricky stuff. But you can see then, ooh. So we take something like that and spin it around the axis, and then we end up with some weird shapes. This one in particular could have been done using washers. However, it is easier to use shells. You would get the same answer, just a different approach. And that's going to be the biggest challenge, is when the problem doesn't tell you what method to use, you're going to have to figure out which method is going to work better and or be easier.
But no matter what, they will work.
Yeah, no matter what, you're going to get the same answer. So here's a shell, and I labeled a bunch of distances on there. R1 is the distance out to the outside of the shell. R2 is the inside radius. The thickness of that shell is delta R. And then I have over on the left there just R labeled. R is the distance to the center of the shell. This being calculus, what do you think we're going to do with delta R? Say again, Ben? Bring it down to dr or dx or dy, depending on what shape. We're going to shrink it down to 0, in other words. So now we do a bunch of algebra, and I don't think you need to write the following down, but I do want you to see where this comes from, and eventually we're going to get it into something that's a little bit more approachable. So there's a whole bunch of geometry going on here. The pi r1 squared h is the volume of the outside shell. The pi r2 squared h is the volume of the hole in the middle. If you subtract those two, then that gives me the volume of all the red stuff that makes up that shell. Then I did a bunch of algebra. Okay. So in this algebra is irrelevant, but this is the difference of perfect squares, so I factored it. I broke some things up, and this doesn't make any sense. Where is all this stuff coming from? I have a 2 and a 1/2 in there. Why is that there? Because I want to get to this. R1 plus R2 divided by 2 is the average radius. That's the same thing as the little r in that picture. Therefore, I don't care how thick the shell is. Obviously, we're going to have that thickness go down to 0 because it's calculus. But I can work the problem without having to know how thick it is because now I know an average radius. And all that stuff there just gets me to that. And as I said, R1 minus R2 is the thickness of that thing. So, what does that mean? Well, you put that all together, and the volume of that shell is 2 pi h times the average radius times the thickness. For our purposes, we're going to take a different approach. We're going to do 2 pi times the area of the rectangle. Okay. Where did the area of the rectangle come from? The area of the rectangle came from delta r times h, the thickness of the rectangle times the height of the rectangle. Average radius is the distance away from the axis of revolution, which we called r in that last picture. Good enough. Okay. Then you add all those puppies up, because you can find the volume of one shell. You use the integral as an accumulator, and you get that. For those of you that are formula memorizers, that's the one you're going to use. X is the distance away from the axis of revolution. Most of the time it will be x, but sometimes it will change, and you'll see that in the examples I have for you. Then this f of x dx is the area of the representative rectangle. F of x would be the height, dx would be the thickness. That's the r, which in that formula is the x value. It's the distance to the center of the rectangle. The x is the distance away from that. When you draw in your representative rectangle, it's the distance from the axis of revolution to that representative rectangle. Then the f of x times dx is the area of that rectangle. And again, this will make a little bit more sense when you see it in motion in the next example. Are we good?
Yes.
Beautiful. Okay, so here we go. I've got a parabola. What can you tell me about that parabola? It's opening down. That 6x is going to do something weird to it. What about the line y equals 0? Also known as x-axis. Okay, so we get that picture. The blue part is the bounded region we're talking about. It's an upside down parabola. It's got x-intercepts of 0 and 6. And then you'll see inside that region I have a representative rectangle. We're going to spin it around the y-axis. So the information I need, 2 things. How far is this rectangle away from the axis of revolution? I have that labeled as x. What's the area of that rectangle? And that would be the height times dx. How tall is, well, I already have it labeled in there. That rectangle is 6x minus x squared tall. And I'm taking rectangles from where to where? Well, the first rectangle I hit is at 0. The last one I hit is at 6. And notice the size of the rectangle starting at 0, very tiny, in fact, infinitely small. Gets bigger and bigger and bigger till it gets the biggest rectangle at 3 and then shrinks back down to 6. None of which I care about because the integral will take care of all of that when you plug and chug. Now, you put all that together. Height of the rectangle, as I said, is 6x minus x squared. The area of the rectangle is that height times the width, which we want really skinny, dx. It's x units away from the axis of revolution. therefore, we get that. By the way, 3 dots means therefore, you know that, right? Good. Now here's the problem with memorizing. You see now the big difference, or not even big, the subtle differences between the formulas. So we've got a formula that's pi r squared. We've got another formula that's big R minus little r. Sorry, I lied. Big R squared minus little r squared times pi. Now we've got another one that's got a 2 pi x times f of x dx. So if you're a memorizer, it could cause some problems keeping those formulas straight. I would argue that this explanation is going to be more helpful than just memorizing the stuff in the rectangle, even though it's important because it's in an orange rectangle. Okay. Multiply out the integral, or integrand, I should say. Those are easy antiderivatives to take, plug and chug, and I didn't even bother with the answer there. I stopped because it's not too bad. Okay. Are we doing okay so far? Good. Let's ramp it up a little bit. We're going to ramp it up a little bit by spinning it around an axis that's not the y-axis or the x-axis. So, and I'm going to take you through some self-talk here, like I started mentioning on Friday. How I process this to figure out what form I'm going to use. Okay, so here's my setup. I've got a parabola that's shifted up 2 units. I've got a line with a positive slope with a y-intercept of 4, and I'm going to revolve it around the line x equals 5. So the big black dotted line over on the right is my axis of revolution. So my self-talk goes something like this. After I've drawn in my representative rectangle, I drew a vertical representative rectangle because I would rather work with x's whenever possible. That's just my thing. This one you can do in terms of y, also it doesn't matter. But anyways, I have a vertical rectangle. Question number 1, is my representative rectangle parallel to or perpendicular to the axis of revolution? Say again? Parallel. As soon as you know it's parallel, you know you're doing shells. And we're moving on from there. Friday I talked about the other self-talk, if it's perpendicular, is it touching or not touching, all that other fun stuff. But this one's pretty straightforward. I need to know 2 things. I need to know the area of that little blue rectangle, and I need to know how far that blue rectangle is away from the axis of revolution. If I can do those 2 things, I can solve the problem. Faith, you got some answers for me?
I don't, but let's say that we did like it this way, then when we do perpendicular, we would use shell.
It would be a washer. But you'd have to do 2 integrals because notice when you get down to this point at -1, 3, the left-hand function changes now all of a sudden. So this one's easier to do in terms of shells, in my humble opinion. Okay, so question number 1. What's the area of that blue rectangle? It's dx thick. How tall is it? Right, good. You can all read. Do you all understand where the x plus 4 minus x squared came from? Oh wait, that's a typo. Hold on. It should be x plus 4 minus x squared plus 2. I'm missing a plus 2 in the picture. I copied down the wrong function. Where did that come from? We're falling back on the same idea we've talked about already. That is simply top minus bottom. Right? So we have the area of the blue rectangle. How far is the blue rectangle away from the axis of revolution? Now, before you answer, let's back up. If I was spinning around the y-axis, then this distance would be simply x. Okay? Because that distance is, I chose to put it there, so I call that distance x. This is not going around this axis, it's going around the axis x equals 5. So the question is, how far is it away from x equals 5? Now we fall back on the same mantra before. Right minus left. The right is the line, 5. The left is the location of the representative rectangle, which is x. So therefore it's 5 minus x units away from the axis of revolution. That's the hard part. Do you see that? Good. So, height of the rectangle. Area of the rectangle multiplied by the thickness, or the width, I should say. Distance away from the axis of revolution. And again, remember, I chose where to put that representative rectangle, so therefore I'm calling that location X. To find the distance from the axis of revolution to the representative rectangle is, again, right minus left, because that's at X. And that's where the 5 minus X comes from. Okay, so if I put this representative rectangle somewhere else, okay, let's suppose I put it over here. It's still going to be the same height. It's still x plus 4 minus x squared plus 2. It's not a numerical value, it's an equational value. And the distance is still going to be 5 minus x because it's the right minus the left, and I chose to put that at x. Okay? I'm taking rectangles from where to where? Well, my rectangles are vertical, so therefore I'm dealing with x coordinates. I'm going to take my first rectangle at -1. I'm going to take my last rectangle at 2. So therefore I end up with, found the points of interest. They were already on the picture, so I didn't need to do that. I'm just showing off. Okay, that mess. So let's review what each of these things represent. This is the 2 pi from doing a shell. This is my distance from the axis of revolution we talked about already. This is the area of the rectangle. And I'm taking rectangles from -1 to 2. This one would not be a fun one to solve. Because you have to multiply it out. I don't know if I did that or not. Let's see. Oh, I did. Oh, yeah. It's a cubic, which would give me... Oh, I skipped that. I think I wimped out there and didn't go any further. So, fn int. Or 1/4 x to the 4th minus 2x cubed plus 3/2 x squared plus 10x. Put in 2, put in -1, get an answer, multiply by 2 pi, answer. Okay, whose head is ready to explode? Awesome. Awesome. Then let's keep going.
Oh, sounds good.
What else can we do? Let's look at that guy. Woo!
Now that's shitty.
This one is actually easier than the previous one. The only thing that makes this difficult is I've got horizontal rectangles. Or a horizontal rectangle. Which means that I need to work in terms of y. However, the function is already given to you in terms of y.
Thank goodness.
Yeah. Everything else you need is in that picture. The size of that rectangle is 2y cubed minus y to the 4th times dy. That's the area of the rectangle. It's y units away from the axis, because I just chose to use the x-axis to make life easy. And where can I take possible rectangles from? My first rectangle would be at 2, because again, we're working with y's, all the way down to 0. When you do that, you get that weird looking donut-y thing, kind of thing. So was it? If you'd like, sure, go ahead, give it a shot. Or did you shout at things? You have like math Tourette's? You shoot out math? Okay. What's the area of the rectangle? How far is the rectangle away from the axis of revolution? Both of those questions are answered in the picture there. That times dx. Or dy, sorry, we're just walking. That's the area of the rectangle. The distance distance away from the axis of revolution would be y.
It's top minus right minus left. There's no left is just
Area is just an equation to bring your
Why you go away from the
Yeah.
distance.
Zero to two is giving
It's about y minus
How do we find the other
Remember, it's sliding up and down, not up and right.
Wait, what are the two area and
Y times 2
find the area?
That's the area.
Yeah.
That's the area of the rectangle.
What do we find else?
The distance away from the axis of revolution, that which would be y. That distance there.
Because there's an equation there,
Why do we need the height?
I didn't see the y.
The height is the thickness of the rectangle. Don't think in terms of height like this way because you just happen to be working horizontally. The height is the thickness of the rectangle. Okay, so that wraps that up. Now, spend the rest of the period then going back to the Fisher-Price cup problem and realize that if you were working on the, well, when you were working on the problem earlier, things should have been in terms of y because you had to do horizontal rectangles. One of those regions is just a rectangle. The other region is the space between the line x equals 2 and the function. Requires two different integrals. That same problem, however, can be done with one integral using the shell method. We'll talk a little bit more about that problem tomorrow. The first two problems that I gave you involving the spacers on the Mercedes-Benz, the solutions are posted on Schoology if you want to go back and look at them.
Where are the equations?